Alright, let's talk a little more about ideals. So we're going to prove some things about prime ideals and inclusion, and these are sort of interesting, I guess. So let's say we have some ideal A, any ideal in a ring, A for abelian. These are commutative rings because from now on those are really the only ones we care about. So we have an ideal A, and we have prime ideals P1 through Pn. Then if A is contained in the union of the prime ideals, then A is contained in one of the particular prime ideals. So the way that we're going to prove this is we're going to actually prove the contrapositive. And the contrapositive is that if A is not, if for every single j from 1 through n, A is not contained in Pj, then A is not contained in the union of the pi's either. I.e., there is some element which is in A, which is not in the union of the pi's. That's the same as saying that that's equivalent to A not being contained in the union of the pi's. And this fact is often called prime avoidance because if you can avoid every single prime ideal individually, then you can avoid the union of the prime ideals. So we prove this by induction. So we start with n equals 1, and we only have one prime ideal. So if A is not contained in our single prime ideal P1, then there must be some element, lowercase a, in the ideal A set minus P1, because that's what it means to not be contained in here. But that's exactly what we're looking for. So the base case is easy. So now for the induction argument, suppose that this fact holds for a particular natural number n. So of course n is not 0. Just to make my writing quicker, let capital I be the collection of indices from 1 to n plus 1. And suppose that we look at this collection of ideals P1 through Pn plus 1, which are all prime, and suppose that we have an ideal A, which is not contained in Pj for every single j from 1 through n plus 1. We want to prove that A is not contained in the union of the pi's, and in particular that there, or equivalently, that there is an element which is in A but not in the union of the pi's. Alright, so how do we do this? For every single index I, choose some element which is in AI but not in Pj for every index other than I. Every index from 1 through n plus 1 other than I. So how many indices are there here? There are n of them because we're taking the n plus 1 indices and removing one of them, so we just have n indices. And so we can do this because we're applying the inductive hypothesis here. So that's how we can choose all of these AIs. So every particular AI is not going to be in AJ whenever j is not equal to I. So if for any I it turns out to be the case that AI is not contained in Pi, then that particular AI is not going to be in, well, it's not going to be in AI, it's not going to be in Pi, but it's also not going to be in Pj for any other index j. And so it's not going to be in any of the Pj's. And so therefore it's going to be in A but not in this union. And therefore it's going to be the desired element. Right? And right, so AI is obviously going to be in A because for every single thing it's in A but it's not in that. Yeah. So it is in A. And so it's in A, but it's not in the union of the pi's, and so it's a desired element. So let's assume for contradiction that we cannot find such an AI, i.e. assume for contradiction that for every single index between 1 and n plus 1, AI is in PI. And we're going to arrive at a contradiction, and of course contradiction arguments, you want to avoid them when you can. Here I don't know if there's a quicker way to do this. And this one isn't too bad. So anyways, let's take our element A and suppose that A is equal to the product of A1 through AN plus AN plus 1. So it turns out that this element, this is going to give us a contradiction. So suppose A is in, hold on, let me look at this. All right. So where is this A going to be? What we're going to do is we're going to assume that it's in some PJ. Basically, we're going to prove that this element cannot be in any of the PJs. And why is that an issue here? I'm blanking on this really quickly here. So let A be this product plus this other element. Right. So, wait a minute. This might not be an argument by contradiction. We know that, okay. So let's see here. So let's suppose that AI is in PI for every single I. I think what we're going to do here, yeah, okay, so this isn't going to be a contradiction. This is actually going to be the element that we're looking for. Because certainly this element A, this is going to be in fancy A here, the ideal A, and that's because A1 through AN, these are all in A, and AN plus 1, that's in A, and products of things in ideals and sums of things in ideals are in the ideal, and so A is going to be in the ideal. And then let's see here. So I'm going to erase this and I'm going to come back to what this should say. So anyways, so what we do is we say if A is in, so we're going to prove that that this element that we've chosen cannot be in any particular PJ. So suppose A is in PJ where J is strictly less than n plus 1. So suppose it's in PJ where J is between 1 and n. Then if we move the product over to the other side, we can write AN plus 1 as A minus this product. But A is in PJ, we're assuming that, and this product of A1 through AN, each of these were chosen here. Oh, no. Since we're supposing that AJ is in PJ, and so AJ appears in this product. And since it's an ideal, multiplying AJ on the left and right by some of the other AIs, you're still going to stay in the ideal PJ because it's an ideal. And so this is an element in PJ minus another element in PJ, and so this whole thing is in PJ. But that's impossible because we've chosen AN plus 1 to not be in PI for any I which is not n plus 1, in particular for I equals j. So we chose AN plus 1 to not be in PJ, and so we have a contradiction. So if it were the case that A were in Pj for any j less than or equal to n, then we'd get a contradiction. We'd get a contradiction, and therefore A cannot be in Pj for j less than or equal to n. What about for Pn plus 1? If A were in Pn plus 1, then we, instead of subtracting the product over, we subtract the an plus 1 over. And so we see that this product is equal to A minus an plus 1. But A we're assuming here is in Pn plus 1, and we've supposed that an plus 1 is in Pn plus 1. So then this thing is in Pn plus 1. So we have this product of A1 through An contained in Pn plus 1. But this is a prime ideal. And so for this to be contained in Pn plus 1, that implies that one of the factors must be contained in Pn plus 1 because this is a finite product. So that is, AI is contained in Pn, AI is an element of Pn plus 1 for some I which is less than or equal to n. But that's impossible since each of these AIs were chosen to not be in the other indices. And in particular, if I is less than or equal to n, then AI is not in Pn plus 1. And so therefore, what we can prove is we've proven that A is not in Pj for j less than or equal to n plus A. We've proven that A is not in Pj for j less than or equal to n, and we've also proven that A is not in Pn plus 1. So therefore, A is in, well, we said that it was in the ideal A, but it's not in the union from 1 to n of, to 1 to n plus 1 of Pi. Okay, so either we're going to have some index I such that AI is not in Pi, and in which case that particular AI will be the desired element that we're looking for, or it might be the case that AI is in Pi for every single index I, in which case we construct this element A which is in A but not in the, that should be a union, getting ahead of myself, which is not in the union of the PIs. All right, and so in either scenario, we found an element. We found an element in the desired set, and that completes our proof. So really glad I was able to save that proof. I was a little worried there. All right. So now we have another proposition. This is sort of a similar flavor, but it's not quite as tricky in my opinion. Because here we had to be a little finicky with the indices. But here, so we take ideals A1 through AN in A, just any ideals, and we suppose P is a prime ideal. Then if the intersection of the AIs is contained in P, then there is some index j from 1 through n such that AJ is contained in P. And furthermore, what I mean by equality implies equality is that if the intersection of the AIs is equal to P, then there is some j such that AJ equals P. So let's prove this. We're first going to prove the statement for inclusions. And again, like the previous proposition, we're going to prove the contrapositive. So if AJ is not contained in P for every single j, then we want to prove that the intersection of the AIs is not contained in P. So for every single, since AJ is not contained in P for all j, we're assuming that, then for each I, we can choose an element AI which is in AI but which is not in P. And then we look at the element A, which is the product of A1 through AN. So here the element construct is a little more intuitive than this one. This one's a little strange. And I wonder with this one, because we actually only used primeness here on A1 through AN. So I wonder if this argument actually works if you've got these ideals here, but you allow one of these ideals not to be prime. And then you choose that one to correspond to this one here. I don't know if that works. I haven't sat down and tried to work out the details. And honestly, I don't think, like, from a mathematical perspective, it is good to try to prove the most general statements that you can. If you can prove the same result using fewer assumptions, then it's good. But, I mean, is it really that much of an improvement to take one of these and make it not have to be prime? I mean, it certainly is a non-trivial improvement, but I don't think like it's enough to warrant me spending a lot of time trying to think about it, or me spending a lot of time on this video trying to discuss it. So let's get back to this proof. So we take A to be this product, and so then A has to be in this intersection, and why is that? I think that's just because these are ideals. Right, so each particular AI is an AI, and so so AI will appear in here, and so this is just AI multiplied on the left and right by elements in the ring, and since AI is an ideal, you'll stay in AI. And so this product is in the ideal AI, and that holds for every single I, and therefore A is contained in the intersection of the AIs. However, if it were the case that A were contained in P, then by primeness, one of the AIs would have to be contained in P, but that contradicts the fact that each AI is not contained in P. And so therefore, by primeness, we know that A is not contained in P. And so therefore, we found an element A which is in the intersection of the AIs, but it's also not in P. And therefore, we've proven that the intersection, so it cannot be the case that the intersection of the AIs is contained in P. And so we've proven the contrapositive statement. As for the equality statement, if it happens that the intersection of the AIs is equal to P, then in particular the intersection is contained in P, and so we can use the first thing that we proved to show that certainly there is some AJ such that AJ is contained in P, but then for the reverse inclusion, P is equal to this intersection, and certainly this intersection is going to be contained in every single particular AJ, or every single particular AI for I between 1 and n. And so choosing that index to be j, we get that this intersection is contained in AJ. So AJ is contained in P, P is contained in AJ, so P is equal to AJ. So that proves that equality here implies equality here. All right, and that's the second proposition. Now just some quick things here. The universal property for rings. So sometimes you go into a little more detail on this, and a lot of times you actually prove this. We didn't prove this. Maybe it's because it's like a very standard thing that you typically see in ring theory, and he just didn't want to spend time on it. But anyways, so given a ring homomorphism F from A to B and an element B in B, there exists a unique ring homomorphism EV for evaluation depending on F and B, which will take us from polynomials in A into B, which is given by, it will take this finite sum of powers of x with scalars in A to evaluating f at the scalars and then replacing x with b. And let's see here, we say that the element b is transcendental over A via f if the kernel of this map is 0. And otherwise b is algebraic. So typically the way you think of this is you let A equal b and you let f be inclusion, so that the scalars here just stay the same. And so what this map is you're just taking a polynomial and plugging in a value. So to say and that's why this corresponds with our definition of like transcendental numbers and algebraic numbers. If you let A and B be the rationals, then what this is saying is, and FB inclusion, or FB the identity map, then to say that a map is transcendental means that there is no a number is transcendental if there is no polynomial with rational coefficients and no rational number such that you plug that rational number into this polynomial and you get 0. Right? Is that how this works? It's whatever it needs to be. Otherwise, B is algebraic. B is algebraic means that there is some in this scenario, it corresponds to this number being a root of a polynomial with rational coefficients. And so that's where you typically see this. Introducing this f and allowing us to use like arbitrary rings here, A and B. This is sort of like, I don't know, I think I mentioned something like this previously, but it's like you could do this. Like this is more general, so it is mathematically speaking better, but I don't know if it adds that much. I haven't really seen this used in a way that makes it useful. Maybe when you get to things like category theory, I think this becomes like something that you actually think about. But for right now, this is it's easiest to think about this as A being equal to B and the map F being just the identity map, so that this becomes just evaluating polynomials at a particular point. And that finishes this lecture.